In this video, we're going to derive an equation for how the coexistence curve for two phases in equilibrium will change as a function of changing either the temperature or the pressure. So we have two phases that we've assumed to be in equilibrium, phase alpha and phase beta. They each have a chemical potential mu, which is a function of temperature and pressure. So at a given temperature and pressure, in order to be in equilibrium at a coexistence curve or a phase change, the chemical potentials have to be equal to one another. So we want to see how we can predict how this equilibrium changes if as a function of the temperature and pressure. So we have a function of T and P, so we can define the derivatives or the total differentials of mu A or mu alpha and mu beta as a function of the change in temperature and pressure. So let's say we have partial derivative of mu alpha with respect to temperature at constant pressure times change in temperature dt plus d mu alpha with respect to pressure constant temperature times the change in pressure. That is going to be equal to d mu beta, corresponding quantity for phase beta, with constant p dt plus partial derivative with respect to pressure at constant temperature at times the change in pressure. Okay, so we have these, and for the individual phases, we know that mu alpha is equal to the molar Gibbs energy of that phase. And we know that the derivative of the molar Gibbs energy for a phase with respect to temperature, based off of the form of it, as we've shown in previous videos, the change in the molar Gibbs energy of a phase with respect to temperature is equal to the negative molar entropy of that phase. And the change in the molar Gibbs energy with respect to pressure at a constant temperature is the molar volume of that phase. So we can rewrite our equations that we have up here in terms of these quantities. We're going to have minus S bar alpha dt plus V bar alpha dp equals minus S bar beta dt plus V bar beta dp. And then if you do an algebraic rearrangement of these two sides and you solve for dp over dt, you should arrive at the equation which I'm going to write down here. So get the pressures on the same side, get the temperatures on the same side, factor them out, and then divide by dt. What you should get is that dp divided by dt is S bar beta minus S bar alpha over V bar beta minus V bar alpha. Again, that's just algebraic rearrangement of this equation here. And these quantities are the transition entropy and the transition volume of the given phase change. So as particles flow from either A to B or B to A, this would be delta transition of the molar entropy. This quantity down here, how the molar volume changes during the phase change, delta transition of molar volume. Okay, so this would be suitable enough for a final equation, but we already know that in terms of a given phase change, we can make another simplification. So at equilibrium between these two phases, the transition Gibbs energy, or transition molar Gibbs energy, we know is going to be 0 because the Gibbs energy doesn't change during a phase change. And we know that that transition Gibbs energy, based off of the definition of Gibbs energy, you can also define it as H minus Ts, enthalpy minus temperature times entropy. That is the transition molar transition enthalpy minus T times molar transition entropy. So H is equal to T times delta H is equal to T times delta S. So delta S is equal to delta H over T because this whole quantity is equal to 0. So what we have is that delta of transition S bar equals the molar enthalpy of transition divided by the temperature of that transition. So that leads us to the final form of our equation. Substituting this in up here, we have that the derivative of the pressure with respect to temperature for how this equilibrium, how these coexistence curves change, is going to be the molar transition enthalpy divided by the temperature times the molar transition volume. So if we know during a phase change at a given temperature and pressure what the change in volume is during the transition and what the change in enthalpy is during the transition, so how much volume does it change and how much heat is absorbed or released by the system during the change, that's going to tell us how the equilibrium will change as a function of pressure or temperature. So generally, we can talk about the sign of these terms. So I can talk about the transition enthalpy. So that is going to be greater than 0, aka absorbed heat, when something melts, when something vaporizes, or when something sublimates, solid to liquid, liquid to gas, or solid to gas. It's going to be less than 0 during processes such as freezing. Freezing is going to release heat to the surroundings. During condensation, going from gas to liquid, and during deposition, going from gas to solid. And similarly, we have our change in transition volume, or molar volume. That is going to be greater than 0 for vaporization, for sublimation, for melting. Same processes listed up here. And it is generally going to be less than 0 for condensation, for deposition, and for freezing. So again, we have to note the exception that sometimes this is reversed. For substances like water, it's greater than 0 for freezing and it's less than 0 for melting. So this is generally the case, but sometimes the reverse. But what you'll see is generally these are all the same sign. You'll have, if this is positive, this is positive. If this is negative, this is negative. So generally your transition enthalpy and your transition volume have the same sign. So that's why our phase diagram, as we look at the pressure and temperature, things like our solid liquid, our solid gas coexistence curve, our solid liquid coexistence curve, and our solid gas coexistence curves, these generally have positive slopes of pressure with respect to temperature for these individual curves here. The slopes of those are generally positive. And that's because these quantities generally have the same sign, and temperature, of course, is always positive in this regime here. But for water, water is a notable exception. So for water, during, say, freezing, the transition enthalpy of freezing is going to be negative, but the transition volume of freezing is positive. So for water, this solid-liquid coexistence curve actually goes backwards and has a negative slope for pressure with respect to temperature. So that's kind of what quantities drive what this phase transition looks like. So the Gibbs energy determines where these transitions occur on the phase diagram, but how they change with their equilibrium relative to one another at different temperatures and pressures, that's dominated by these quantities here that we see. The transition enthalpy, the heat, and the transition volume, how it changes in space.